2.2, graphs of functions. A graph of a function is a set of all the ordered pairs x, comma, f of x of the function. That just means that it's all the inputs and outputs put together in one graph. Let's do some examples where we actually graph the functions. The first way that we're going to graph a function is by creating a table of values and then plotting those points. So let's start with f of x equals x squared. So we can pick some values like 0. If we plug in 0, 0 squared is 0. We can also pick 1, plug in 1. 1 squared is 1. And 2, if we plug in 2, 2 squared is 4. It also doesn't matter whether or not these are positives or negatives, so we can actually, just by knowing that, we can double the amount of points we have. Because you plug in negative 1, you'd also get 1. Plug in negative 2. Negative 2 times negative 2 is still positive 4. So let's plot these 5 points. 0, 0. 1, 1. And negative 1, 1. 2, 4. And negative 2, 4. Then basically just connect the dots with a curve to make it look smooth. And there's our graph. For example B, g of x equals x cubed. Pick some points like negative 2, negative 1, 0, 1, and 2. We can plug in negative 2. We get negative 2 times negative 2 times negative 2, so that's negative 8. Let's jump down. When we plug in 2, positive times positive times positive, that would be positive 8. We plug in negative 1, negative 1 times negative 1 times negative 1, that's negative 1. Plug in 0 is 0, plug in 1, you get 1. So if we plot these 5 ordered pairs, x, g of x, we'll get an idea of our curve. Negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, and 2, 8. Again, connect the dots with a curve. And there's the graph of our function. For example C, square root of x. We need to pick some values. Now for square roots, we can't take square root of a negative, so we can only take 0 and positive numbers to plug in. So 0, 1, 2, and let's actually skip 2 because square root of 2 is going to be too hard to graph. So we'll go 0, 1, jump up to 4 because there's a square root, and then 9 because there's a square root of 9. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and the square root of 9 is 3. Plot those points. 0, 0, 1, 1, 4, 2, and 9, 3. Since we can't go into the negatives, we're not going to draw the graph at all in the negative side of x. so just on the right side of the y-axis. And it should be a curve that goes through those points. For our next example, we're going to graph a piecewise function. Remember, piecewise functions are just split up at a certain point. So I like to think of a imaginary line at those points. I'm going to go ahead and draw one in at x equals 1. Just as a reminder that there's a break in the graph there. So it is x squared if x is less than or equal to negative 1, or sorry, positive 1. We graph x squared. We know from our previous example that x squared would go through all of these points. 1, 1, 2, 4, also on the negative sides. But this is only for x less than or equal to 1. So anything that would be on the right side of the graph we don't count. Since it is equal, we do count the point right here at 1. But then draw your curve. Now we have half of it for the other part of the piecewise function. 2x plus 1 if x is greater than 1. 2x plus 1, we can plug in some points if we want. We can plug in things to the right of 1. We can plug in 2, 3, 4, as many points as we want. If we plug in 2, 2 times 2 is 4 plus 1 is 5. So 2, 1, 2, 3, 4, 5. When we plug in 1 just to see what it would be, even though that point doesn't count, plug in 1, we would get 3. 2 times 1 plus 1. So there would be a dot here, but it doesn't actually count. So we're going to go ahead and put an open circle because we only use that function if x is greater than, not equal to. Plug in another point. Let's plug in our next point, 3. 2 times 3 is 6, plus 1 would be 7. So we go up to 7, put a dot, and we can draw that line. With the open circle at x equals 1. And the graph doesn't actually include that dotted line, so we can delete that. There's the graph of our piecewise function. Let's take a look at the graph of an absolute value function, where f of x equals the absolute value of x. Now, if you remember, absolute value makes everything a positive, so really it's a piecewise function. It's a piecewise function that we could say if x is greater than or equal to 0, it doesn't do anything, it doesn't change it, doesn't have to change it because they're already positive. But if x is less than 0, it has to change the sign. So we can do that just by saying negative x. The negative would change the sign and make it be positive. So we know that the graph of f of x equals x. We plug in 0, we get 0. Plug in 1, we get 1. 2 to get 2. 3 to get 3. 4 to get 4. And so on. Now when we plug in a negative, plug in a -1, we would get 1. Plug in -2, we would get 2. Plug in -3, we get +3, and so on. So the absolute value function looks like a V. Now let's take a look at the greatest integer function. This is probably new to most of you. The greatest integer function is defined as the greatest integer that's less than or equal to x, the thing that you plug it in. So what that means is for positive numbers, you basically just ignore everything after the decimal. So the greatest integer of 2 would be 2. For 2.3, you get 2. 1.99 will be 1. And then 0.002 is 0. You just ignore anything after the decimal if it's positive. If it's negative, it would just be, the value would increase by 1. For example, the -3.5, -3 would increase, the 3 would increase in value to a 4. So it would be -4. For all of these, it's the integer that would be left of whatever we're plugging in on the number line. -0.5 equals -1, -5.1, that will go to -6, and -7.79 goes to -8. All the values increase by 1, 7 to 8, 5 to 6, 0 to 1, 3 to 4, if it's a negative inside. So let's go ahead and graph, try to make a little table. So anything up until we get to 1, 0 point anything will equal 0. So we'd have a straight line right there, counting 0, not counting 1. And then anything at 1, 1 would be 1. And then anything until we reach 2 would still be 1 until we reach 2, so we don't count 2. When we get to 2, 2 point anything would equal 2 until we get to 3, but it doesn't equal 3. So we start getting what I call I think it looks kind of like a staircase. That's why sometimes we'll call this the staircase function, and so on. And then on the left side for the negatives, you can just really continue the pattern that you see on the right, sticking with the same principle that we just went over. -1 until 0 would equal -1. -2 until -1 would equal -2, and so on. And it's always a closed circle on the left and an open circle on the right for the greatest integer function.